Hello class, welcome to this lesson on looking at the t-test for the mean. So what we want to do in this lesson is we want to look at the t-test and talk about when we use the t-test. Recall that last time we talked about the z-test, which was used when the sample size was large, which was greater than 30. So this time we're looking at the t-test, which is used when the sample size is less than 30. So let's get started. What we want to look at first are the characteristics of the t-distribution. So kind of reviewing what the t-distribution looks like. So the actual t-curve, so if you were to graph the z-curve first, so this is the z-curve right here. So this is the normal bell curve. If you were to draw the t-curve, well, the t-curve is actually more spread out. So this is an example of a t-curve. However, keep in mind that the t-curve has different shapes. And the reason why it has different shapes is because it depends on the degrees of freedom. So if I were to have a t-curve so this t-curve right here means that we have a low degree of freedom, so small degrees of freedom. If we have a larger degree of freedom, well then the t-curve gets skinnier and rather than broader. So then the t-curve will look something like that. So this is a t-curve with a high degree of freedom. So the larger the degree of freedom of the t-curve, the closer it resembles the z-curve. Okay, so the t-curve is essentially a family of curves, and the curve that you choose depends on what your df is, your degree of freedom. So notice that both of these are bell-shaped, and the t-curve is definitely symmetric just by looking at the graph, just by inspection. The mean, median, and mode are at 0 for the standard t-distribution and the standard normal distribution. Looks like the curve never tries to approach the x-axis and never actually crosses. It just approaches it on both sides. So that's a characteristic it has in common. The t-distribution differs from the standard deviation in the following ways. So the t-distribution is more spread out. So if the variance is greater than 1, that means the curve is more spread out. And as we mentioned earlier, the t-distribution is a family of curves, which is based solely on the degree of freedom. So this is a number related to the sample size. Remember that the degree of freedom is calculated by taking the sample size, subtracting 1 from it. As the sample size increases, which means as your df increases, the t-distribution approaches a normal distribution, which you can kind of tell from the basic drawing that I have up here. So then we're going to go ahead and define what the t-test is. So it's a basic statistical test, and it's used to find the mean of a population, and we can use it when the population is normally distributed. Then that's generally the criteria for these tests. So the population has to be normally distributed, or approximately so. And generally we use this when we don't know what sigma is, because if you know what sigma is, you generally can use the z-test. If you don't know what that is, and you generally don't know what it is, and your sample size is small, then make sure that your population is normally distributed before using this test. So the formula for the t-test is given below. Notice it's very similar, except for the fact that we don't know what sigma is, so we use S instead of sigma. All right, and then also note that we have degree of freedom here, and that's the formula for the degree of freedom. Remember that the sample size has to be less than 30 in order to use the t-test. All right, so finding the critical value, if we want to find the critical t-value, then what we need to do is look this up on the t-table. Since we're looking at a right-tailed test, that means we're looking at one tail. So we want to distinguish whether we're looking at one tail or two tails. And then clearly this is a one-tail test. And we need to find out what our degrees of freedom are. But we know that the sample size is 17, so taking away 1 from that, we have 16. And we have our alpha. So the t-table, we don't have to divide by 2 or subtract from 1 from alpha at all. because the t-table already has this built in. All right, so we have 0.05, 16, and a one-tailed test. So we're going to refer to the t-table right here. So our degree of freedom is 16, and our alpha is 0.05, and we're looking at a one tail of alpha. So we're looking at this row. So 0.05 and 16. So it looks like our number is 1.746. All right, so our t value is 1.746. So we'll call this t critical. Now, if it's a right-tailed test, that means the critical value is positive. So we have positive 1.746. If it's left-tailed test, it's negative. So for this left-tailed test, the value is going to be negative. For the two-tailed test, it's going to be plus or minus, since we have both sides of the curve. All right, so then we're going to look up. So we have df is 22. So 22 with an alpha of 0.01. So for part A, we're going to go ahead and find our t crit, but we know it's going to be negative. For part B, same thing, but it's going to be positive and negative. All right, 0.01 and 22. So 22, and for a alpha of 0.01, looks like we have a value of 2.508 for the first one. So 2.508, and then for an alpha of 2 tails 0.01, we simply have this value over here, 2.819. So basically these two values, see how much they change slightly. So 508, 819. All right, and those are your critical values. It's pretty straightforward to find from the table. Now that we know how to do the critical values, we're going to talk about the assumptions for the t-test. So some things that we assume in order to use the t-test, that means the sample has to be a completely random sample. So you have to select your sample randomly. If you don't select your sample randomly, then and you don't do it by chance, then your results are going to be skewed and they're not going to be interpretable in the way that you'd want them to be. The population has to be normally distributed if your sample size is less than 30 for using the t-test. So the population is normally distributed. So those are our two main assumptions here. Now, when you do the project, you will not generally assume this. You're gonna basically do your project, and then when you collect your sample, you're gonna try to make it as random as possible. And then for the second condition, you want to test whether your population is normally distributed. All right, so for finding the p-value, what we want to do is use the t-table, but use it in a way as to find an area instead of a critical value. So what we do is they give us a t-test of 1.32. So we got t is 1.32. Our sample size is 11, so that means our degree of freedom is 11 minus 1, which is 10. And we're looking at a one-tailed test, so one tail. All right, so then what we want to do is look up our p-value from the table. So we're going to get as close to 1.32 as possible with a degree of freedom of 10. All right, so the degree of freedom of 10, we're going to go as close to 1.32 as possible. So that looks like 1.372. So notice that we are on the left side of 1.372. So we're somewhere on the left side, okay? Which means that if we go to the one tail here, we're at 0.10, right? So we're on the left side of 0.10. But look what's on the right side. The right side is 0.05, which means it got smaller on the right side. So that means that if we're going on the left side of 0.10, that means we're going to get larger. So that means our p-value has to be bigger than this value of 0.10. So that means that for the one tail, our p-value has to be larger than 0.10. All right, and that's our answer for the part A. So for part B, we're looking at a t value of 2.983 with a degree of freedom of 5, and we're looking at two tails. So we're going to get as close to 2.983 as possible. So looking at 5 degrees of freedom, we want 2.98-ish. So it looks like it's between these two numbers, that one and this one. So that means if we go to the two-tailed, we are between these two numbers, 0.05 and 0.02. So since we're between those two numbers, we're saying our p-value is between those two. So our p-value is bigger than 0.02, but it's less than 0.05. So we have here that our p-value is larger than 0.02, but smaller than 0.05. All right, so then we're looking at the third one. So we have a t of 3.35 with a df of 12. So we're going to look at 12 and then 3.35 for a one-tailed test. So then for degree of freedom of 12, we have 3.35. So it looks like we're past this number. We're larger than this side. So we're on the right side of 3.055. And if we're looking at a two-tailed or one-tailed test, then we're over here. So we're to the right of 0.005, right? So that means that if you look at the left side, it's greater than. So that means on the right side has to be smaller than. So we have to be smaller than this 0.005. So our p-value smaller than 0.005. All right, so now we're going to just quickly recap the steps for the traditional method and the steps for the p-value method. So for the traditional method and the p-value method, both steps are identical. So these steps are identical. You want to state the hypothesis, identify the claim. The steps that differ are, step 2 and step 3. So step 2 in the traditional, you want to find the critical value, whereas step 2 you want to, whereas in the p-value method, you want to find the p-value. So that's how they differ. So one finds the critical value, the other one finds the p-value. And then the other two steps are identical. So the only steps that differ are the fact that you're finding the p-value for one and the critical value in the other one. So that's the only one that differs. All right, so for the following exercise, we want to use both traditional and p-value methods. So what I'm going to do is I'm going to do all the steps for the traditional method, and then I'm going to just introduce the p-value. I'm just going to find the p-value separately, and then that will conclude both methods, okay? So like I said, the only thing that differs is the p-value method calculates the p-value. All right, so we're going to look at the following problem. So we have a medical investigation claims that the average number of infections per week at a hospital in southwestern Pennsylvania is 16.3. A random sample of 10 weeks had a mean number of 17.7 infections. The sample standard deviation is 1.8. Is there enough evidence to reject the investigator's claim at alpha equals 0.05? Assume the variable is normally distributed. All right, since it's normally distributed, that means we can use the test. And notice that we have a sample of 10 weeks. So that's my n. So n is 10, which is less than 30. So we have here a claim. The average number of infections per week is 16.3. So is an equality statement. So that belongs to the null. So step 1, set up our hypotheses. So this is equal to 16.3. And we want to see, is there enough evidence to reject the claim? So that means that we're going to say is not equal to. So this is our claim. All right, and we want to identify our average. So X bar is 17.7 infections. And the sample standard deviation is 1.8. So this is a sample standard deviation. All right, so then step 2, we want to compute the test value, or we want to actually do the critical value. So let's do the critical first. So we want our degree of freedom. And if we look at here, we're looking at a two-tailed test. So this is a two-tailed test. All right, and so our degree of freedom is simply 10 minus 1, which is 9. So we're looking at 9 with an alpha of 0.05 and two tails. So we're going to find that value real quick. So 9.05, two tails. So two tails, 0.05, and a degree of freedom of 9 means that our critical value is 2.262. Now, since it is a two-tailed test, we have a plus or minus version of the critical. All right, so that is it for our critical. So now our next step, we're gonna compute the test value. So I'll do that over here. So we're gonna do t test. So we're gonna calculate it. So remember the formula as x bar minus mu over s divided by square root of n, and n is 10 here. All right, so we're gonna actually compute the value here. So we got 17.7 minus 16.3. Over 10, and then we want the square root. All right, so then we go ahead and we get a we go ahead and calculated it. So we have a t score of, let's go down real quick. All right, so go ahead and calculate it. We got a t-score of 2.46. All right, so what we want to do is I want to go ahead and draw that real quick, just so that we have an idea of what we're looking at. Remember, our standard deviations go by 1 on each side. All right, and then if we graph our so let's do our critical values first. So that's 2.262, positive and negative. All right, so then we're gonna go ahead and label our rejection regions. I'm gonna shade our rejection regions here. Then we're gonna label, and I'm gonna do this in a different color. I'm going to label my t-test. So 2.46 is over here. And this right here is our 2.262, and this is our negative 2.262. So clearly we can tell that we're in our rejection region. That's a 4 right there. So therefore, we reject. Okay, so step 4 in our decision-making process is to reject. Before we do that though, I want to go ahead and calculate the p-value while we're at it. That way we can take care of 2 birds in 1 stone. So then we'll have both methods in one fell swoop. So we need to calculate our p-value. So to do our p-value, remember we need our degree of freedom, which is 9, and we want to get as close to 2.262 as possible. All right, so then if we're going to go ahead and do that now, so 9, a degree of freedom 9, get as close to I'm sorry, not 2.262, we want our test value. We want to get as close to 2.46 as possible over here. We want to get as close to that number as possible. All right, so 2.46. But if we look at here, 2.46 is between 2.262 and 2.821. So it's between those 2 numbers. So therefore, for a two-tailed test, we're looking at between these 2. So the p-value is between 0.02 and 0.05. Right? So our p-value is less than 0.02, but greater than 0.02, but less than 0.05. All right, and then if we were to look at the decision-making process, well, the p-value is clearly less than alpha, because alpha is 0.05, which means we reject. Okay, so step 4 in our decision-making process, regardless of which method we use, we reject. All right, and then step 5, we write our summary. So since we're rejecting, that means we have enough evidence at the 5% level of significance and then since our claim belongs to our null, we're going to say reject. So we have enough evidence to reject. And then the claim, according to the problem, is that the average number of infections per week at a hospital in Pennsylvania, 16.3. So claim that the average number of infections is 16.3. All right, so going to looking at the next problem. According to payscale.com, the average starting salary for a nurse practitioner is $79,500. A researcher wishes to test a claim that the starting salary is less than $79,500. A random sample of 8 starting nurse practitioners is selected, and their starting salaries in dollars are shown. Is there enough evidence to support the researcher's claim at alpha equals 0.10? Assume the variable is normally distributed. All right, so we know we're looking at only 8 nurse practitioners. So that means our sample size is quite small. So if n is equal to 8, which is less than 30, this means that we need to use a t-test as long as it's normally distributed, which it says assume that. All right, so then it says that the claim is that the average starting salary is that. So step 1, our average starting salary is $79,500. And it says, is there enough evidence to support the researcher's claim at alpha equals 0.10? So actually, in this case, this is not going to be the claim, because it says a researcher wishes to test the claim that the starting salary is less than $79,500. So the researcher wants to test that claim. So therefore, our claim is that, less than $79,500. So in this case, our alternative is our claim. Remember that this is alternative because this does not have an equal sign, whereas H0 has the equal sign, okay? All right, so then for step 2, we want to be able to compute or find the critical value. So for alpha is 0.10, and clearly from this we're looking at a right-tailed test because of the left-tailed test, I'm sorry, because of the less than symbol. So this is a left-tailed test, and we need to find the degree of freedom, which is 8 minus 1. So DF is 7, alpha is 0.10, and we're looking at a one-tailed test. So DF is 7, one-tailed test, alpha is 0.10. So we're looking at a T critical of 1.415. But since we're looking at left-tailed test, it's going to be negative 1.415. And that's our T critical. So now we're looking at computing our T test, which, if you remember, is this formula here. So we need to find out what those numbers are from the data. So we need to figure out what X bar is, and then we need to figure out what S is. So we're going to put that in the calculator in order to calculate those two quantities. All right, so we go ahead and plug that in the calculator. So we got this as our average and this as our approximate standard deviation. I'm going to go ahead and plug those numbers in. Oops, that should not be 6938. So this right here should be our mu, which is our hypothesis, 79,500. That's what we think it is. And then 6938 over square root of sample size, which is 8. All right, so we went ahead and calculated it, put it in the calculator. We got negative 1.77 as our t-test. Now we're going to go ahead and put those on the graph. So we have, also we'll need to calculate the p-value. So let's do that real quick as well. So while we're at it, so for the p-value, we need to remember that we're looking at alpha, or we're looking at df as 7, and we want to get as close to 1.77 as possible. So looking at df of 7, 1.77 is between those two numbers, so it's between these two, which means that for a one-tail test, we're looking at between 0.05 and 0.10. So our p-value is between 0.05 and 0.10. So that's 0.10 there, but greater than 0.05. All right, so then clearly looking at this, if the p-value is less than 0.10, that means that our p-value is less than alpha, because alpha is 0.10, which that tells us that we're going to reject because it's less than or equal to alpha. All right, so that means, but we're going to go ahead and just graph it real quick just so that we have the visual. So we got the negative 1.4 here. And clearly this is not drawn to scale because my graph is not very symmetric, but we'll use it anyways. So we have our rejection regions, and we have our p-value, or we have our t-test is negative 1.77. So we'll do that in blue. That's over here, negative 1.77. So we're clearly in our rejection region. So therefore we can go ahead and reject. All right, so then clearly we're going to reject here. All right, so as we mentioned earlier, this is in our critical region or rejection region, so we reject. And then p-value is less than alpha, so we reject. So that means we have enough evidence at the 10% level of significance to support the claim that the average salary for nurse practitioners is $79,500. All right, and then we're going to look at one more problem, and this one is looking at a claim that the jogger's maximal volume oxygen uptake is greater than the average of all adults. So we're looking at a claim that the oxygen intake is greater. A random sample of 15 joggers has a mean of 40.6 milliliters per kilogram and a standard deviation of 6. If the average of all adults is 36.7, is there enough evidence to support the claim at alpha is 0.05? All right, so then we're going ahead and write out the claim. So first step. So we need our hypotheses. So it says that the claim is greater than the average. And it says that the average is 36.7. So it's saying that the average maximal volume intake is greater than the adult average in general. So this is our claim, and this belongs to our alternative because it's a strict inequality. There's no equals or any bars underneath it at all. All right, and it's saying that the normal, so you can do less than or equal to, or you can say equal to. I'll just use equal to the 36.7. Now, is there enough evidence to support this claim at alpha 0.05? So step 1 is done. Let's go ahead and do step 2. We want to find the critical value. So since we're looking at 15 joggers, n is 15, which is less than 30. We're assuming that it's normally distributed, so we can use a t-test. So we need to find our df, which is 15 take away 1. At an alpha is 0.05. And we're looking at a right-tailed test, since it's greater than pointing to the right. So one tail with degree of freedom 14. So one tail of 0.05, degree of freedom of 14, so that means 1.761 is our critical. And since we're looking at a right-tailed test, it's positive 1.761. All right, step 3, calculate our t-test. So we're going to go ahead and plug in the numbers. So x bar in this problem, from the random sample of 15 joggers, we got a mean of 40.6. And this has a standard deviation of 6 milliliters per kilogram. All right, so 6. So we got 40.6 minus the mu, which is 36.7, over 6 divided by square root of 15 joggers. All right, so if we go ahead and plug it in the calculator, we get about 2.52 for our t-test. We're going to go ahead now and do our p-value. So we want to get as close to 2.52 as possible with a df of 14. So df of 14, we want to get as close to 2.52 as possible, which is between these two numbers, it seems. So that means that for a, we're looking at a one-tail test. So we're looking at one tail, so it's between these two guys. So p-value is greater than 0.01, but less than 0.025. All right, so then that is our p-value. So we're going to go ahead and make our decision. Oh, before we do that, we need our... Okay, so if the p-value is less than 0.025, that means that the p-value has to be less than or equal to 0.05, which is my alpha. So that means we reject. Okay, so we know that we reject, but just so that we can do the graph, because we need to do the traditional method as well, I'm going to go ahead and quickly do the graph. All right, so then we have our critical is 1.761, so it's over here. Go ahead and shade our rejection region. It is a right-tailed test. We're going to go ahead and label our t-test, which is 2.52, which is straight in the rejection region, so that means we reject. So step 4, we reject. All right, which means that we use the phrase, so we're going to use the phrase, we have enough evidence, and since our claim is our alternative, we have enough evidence at the what is it, 5% level of significance to support the claim that the average maximal volume intake is greater than the average for all adults. All right, and that's going to conclude the lesson, guys. I hope you learned something from this. I hope this was also a good refresher if you had already gone over this, and we'll see you guys next time.